Okay, so in this video, we are going to consider the so-called subspace theorem. If you recall our previous discussion, the idea is we have now in our pocket these five larger vector spaces, Rn, Rm by n, R infinity, the space of all real functions, and the space of complex numbers. And the question is, for new examples of possibly vector spaces, can we avoid having to check all 10 axioms? And the answer is yes. So let's look at the definition. We have V is a vector space, and W is a subset of V. So every element in W is an element in V. We say that W is a subspace of V if W, with the same vector addition and the same scalar multiplication as V, is also a vector space. In other words, W is a vector space in its own right. So if you think of it this way, if we say that W is a subspace of V, what we're saying is that W is a smaller vector space living in the larger vector space V. And here where it's interesting, if we, and this will be the proposition, suppose that we already know that V is a vector space, and we have a subset of V. And for a lot of our examples, V will be one of our known five larger vector spaces, as I've just said, Rn, Rm by n, the space of all real sequences, the space of all real functions, and complex numbers. V will usually be one of those five, and then we'll have a subset of the elements that we know are elements of V, and we're going to ask, is W a vector space or not? And the great thing is we could be naive and check all 10 axioms. What the subspace theorem says is we only have to check the first two axioms, the two closure axioms. So here's the statement. If W is a subspace, so W, is a subspace of V, therefore a smaller vector space living in the larger vector space V, this is the case if and only if W satisfies the two closure axioms. It is closed under addition, so if we take any two elements of W, the sum is still an element of W, and closure under scalar multiplication, if we take any real number and any element in W, then the new element, lambda times u, is still an element of W. And you see the word closure means that the space is closed under addition and scalar multiplication. So by adding elements of our space, we cannot leave the space. Take two elements of the space, if you add them up, it's also in the space, and it's also closed under scalar multiplication. No matter which element you take in your space, which real number you take, the new element, lambda times u, will always be in the same space. And this is great because if we know V is a vector space, and W is a subset of V, and we want to prove that W is a vector space, we do not have to check all 10 axioms, only the first two, the two closure axioms. Before we look at this fact, let's ask ourselves, why is this actually true? Let's go back to the list of 10 axioms. We will assume that W is a subset of a known vector space V and show that the other 8 axioms are automatically true in W, just because W is a subset of V. So here are our 10 axioms. And remember what we had. V was a vector space, so we know the elements of V satisfy these 10 axioms. And now we will consider a smaller space living inside of V. So let's draw a picture. Suppose that, and it's kind of hard to draw an entire space of generalized vectors. So here's how I usually draw it. Think of this space, this giant egg, being the entire space V. And now W is living inside of V. It's a subset. So think of this smaller egg being the set W, right? W is a subset of V. Therefore, every element of W is an element of V. So W is a space living in the larger space that is our known vector space V. Let's check why we have to check absolutely these two axioms. The axiom says if you take two vectors in V, the sum is still in V. So we know that any two vectors we choose in V, and I'll try to imagine the vectors as being simply points. If you take any 2 points in V and you add them up, you know you'll get a new point in V, a new vector. But think of it. What if I take a vector in W, another vector in W? Because these two vectors that I'm visualizing as just points in the space, but because these two vectors are in V, and we know V is a vector space, we know that if we add two vectors from V, the result is still in V. But think about it. So we know that if we add these two vectors together, the result will be somewhere in V, but it may not be necessarily in W. Maybe I add these two vectors and I end up here, or maybe I add these two vectors and I end up here. So even though the sum of these two will always be inside of V, the sum may not be outside of W. It may actually lie outside. And so you see that the first property, closure under addition, may not be necessarily true of W. It could be false. You could take two elements from the subset W, the sum lying in V but outside of W. So we have to check the first axiom. Let's look at closure under scalar multiplication. This says take a real number, lambda, and some vector in your space. If you multiply your vector by lambda, it is still a vector in your space. So imagine this. Suppose I take this vector in W, and I multiply it by some real number. We know because V is a vector space, the result will be somewhere in V. Well, you could be lucky and multiply this vector in W by a real number and have a new vector, say this one, in W. But you can multiply this vector by some other real number, and the result may actually lie somewhere in V that is outside of W. So W does not obviously satisfy the second property, so it has to be checked. Well, so far we're off to a rather rough start. Let's look at these properties, and this is where it gets interesting. We are saying everywhere in V, U plus V is the same as V plus U, so addition commutes. So this says take any two elements of your space, and you can add them in opposite order, the result is still the same. So think about it. Everywhere in V, U plus V is V plus U. Well, if U plus V is V plus U everywhere, clearly it's true in here. So automatically, property 3 is satisfied in W because it's satisfied everywhere in V, and W is inside of V. So clearly, because this property is true everywhere in V, and W is a part of V, it has to be true here. So we do not have to check the third axiom. Same for the fourth axiom, right? This property holds for any choice of three vectors in our space V, U, V, and W. Addition is associative. But think about it. Addition is associative everywhere in V. So we have associativity of addition everywhere in V. So if it's true everywhere in V, clearly it has to be true here in W. So we do not have to check property 4 in W because it's actually inherited. Property 5, I'll skip for now. Same for property 6. Let's look at properties 7, 8, 9, and 10. And we'll kill all of them in one go. Look at these properties. We're saying that for any choice of real number or real numbers and vectors, these algebraic equalities are true everywhere in V. For any choice of vectors in V and real numbers, these are always true. 7, 8, and 9. And the same thing for 10. Multiply any vector in V, say U, by 1, the result is always U. These are just algebraic properties, and they are true everywhere you look in V. So clearly they're true in W. So we don't have to check property 7, property 8, property 9, property 10. They are inherited automatically in W because they are true everywhere in V. Now we're talking. We're down with 2 axioms. Do we have to check these 2 as well? Now here, because I'm looking for a very intuitive discussion of vector spaces, not a very technical one, I will actually be sweeping 2 technicalities under the rug. So what I'm about to say is slightly incorrect, technically, but the intuition actually holds. But be careful, keep this in mind, that there are really here 2 technicalities that I'm sweeping under the rug to try and keep this discussion rather intuitive and not too technical. Let's look at property 5 and 6. Assume that we have our subset W of V and that we have proved that properties 1 and 2 hold. We know that because properties 3, 4, 7 through 10 hold in V, they automatically hold in W, and we don't have to check them. But suppose we do have proved that properties 1 and 2, axioms 1 and 2 hold in W. Can we intuitively see that properties 5 and 6 will hold as well? And as I said, I will be hiding here, sweeping 2 technicalities under the rug, but the intuition is correct. Think a bit. Let's use property 2 to prove property 5. And again, really, really important, my proof is flawed. It really is just a heuristic argument. Technically, this is incomplete. Property 5 says that there must be a 0 element in your space, so that if you add the 0 element to any vector, the result is the same vector. And if you think of it, well, how do we know if the 0 vector is in W? The 0 vector is somewhere in V, but it could be outside of W. But suppose that property 2 has been proved to be true in W. What does it say? Take any real number, take any element of W, multiply the vector by the real number, the result should still be in W. So imagine yourself taking this vector. Let's call it W. And any real number times W should still be in the space W. So if you think of it, why not take the real number 0 times the vector W? And this is where I'm being slightly hand-wavy. If you use your intuition, if you multiply any vector by the real number 0, the result should be the 0 vector. Intuitively, this makes perfect sense. Technically, you would have to prove this. And the proof is again very technical, and I want to keep this discussion intuitive, so we'll just take this for granted. If I multiply some vector by the real number 0, the result intuitively should be the 0 vector. But now think of it. We assume that we had closure under scalar multiplication in W. So for any real number in any element in W, well, here's a real number, here's an element in W, the product of the vector by the real number has to be still living inside of W, because W is assumed to be closed under scalar multiplication. And so you see that the 0 vector is an element of W. Again, this is just an intuition. It technically does require proof, but we're going to skip it. So if we use our intuition, if property 2 is true, automatically property 5 is also true. Okay, what about property 6? Once again, we are going to here use an intuitive argument. Technically, this does require proof. If you think of it, we're going to say, okay, we have an element in W, and now let's multiply W by the real number -1. And intuitively, if you think of it, we know that because W, assuming we proved, was closed under scalar multiplication, if we multiply any vector from W by any real number, the result has to be an element of W. And if you use your intuition, if you multiply a vector by the negative real number, by the real number -1, intuitively you should get the negative element, negative W, which lies in the space by the assumption that we had proved closure under scalar multiplication. And so you see, intuitively, if W, the vector W, is in the larger space, and W, the space, is closed under scalar multiplication, the negative element of W will also lie in the space. And therefore, using this intuition, if property 2 is true, property 6 is also automatically true. And so you see, if you have a known larger vector space V, and you have a subset W of V, to prove that W is a vector space in its own right, one simply has to prove axioms 1 and 2, the two closure axioms. Axioms 3 to 10 are automatically satisfied. And that's the beauty of the subspace theorem. Let's look now at the important fact that was mentioned as a consequence of the subspace theorem, and we will prove this using, of course, the subspace theorem. And this should look familiar, at least the span. What this says is the following. If you take V to be any vector space, so a space that satisfies the 10 axioms, if you take any number of vectors, say n of them, v1, v2 through vn, in V, then automatically if you take the span of these vectors, so the set of all linear combinations of these n vectors, this will always be a subspace of V. Therefore, the span of vectors from a vector space will always be forming itself a vector space. And let's prove this using the subspace theorem. And then we can use this result every time that we can. If we ever have a set that is the span of any number of elements that we know are from a known vector space, the span is automatically a vector space itself. Alright, so let's prove it using the subspace theorem. By assumption, V is a vector space, and so if we take linear combinations of these elements, we will always get vectors in V, because V is closed under addition and scalar multiplication, so clearly W is a subset of the vector space V. Therefore, to prove that W is a vector space, we only have to prove that W is closed under addition and scalar multiplication. So let's prove that. Well, okay, what is the span of any number of vectors? So V1, V2 through Vn. As we have just said, the span is by definition the set of all linear combinations of these n vectors. So it will be the set containing some multiple of V1 plus some multiple of V2 up to some multiple of Vn. And because we take the space of the set of all possible linear combinations, the coefficients C1 through Cn are allowed to range over all real numbers. So Ci from 1 to n is allowed to range over all real numbers. So let's prove that W is closed under addition and scalar multiplication. So the first axiom, closure under addition. Well, what is closure under addition? It says take two elements of your space. So here's what we take. Well, our space is called W, so we can call the element, say, lowercase w1 and lowercase w2 to be two vectors in our space. And again, the word gives it away, closure under addition. So if we add these two vectors, the new vector is still in W. That's what we want to show. So we take an element from our space W1, we take an element of our space W2, and if we add them up, our space is closed under addition, and so the sum of these two vectors will also be in our space. So let's prove this. Well, what are the elements of our space? They are linear combinations of these fixed n vectors. So what do we know? Because W1 is a vector in W, it must be a linear combination of these n vectors. I will use A1, A2 up to AN for the coefficients. So there must exist a set of n real numbers A1 through AN so that W1 is a linear combination of these n vectors. The same goes for W2. W2 is also in the larger space W, therefore is a linear combination of these n vectors as well. And I will call the coefficients of this linear combination B1, B2 through Bn. And now let's add W1 and W2, and I will add them putting together the multiples of V1, right? So W1 plus W2 equals, well, we know addition commutes, so we can add the vectors, so these plus these in any order that we want. I'll add these two together, and I will factor the A1 plus B1. So this will be simply A1 plus B1 times vector V1, plus I will add these two together and factor V2, and have A2 plus B2 times V2, up to, adding these two together and factoring Vn once again, An plus Bn times Vn. Well, why is this interesting? Well, look, W1 plus W2 is some real multiple of V1 plus some real multiple of V2 up to some real multiple of Vn. Therefore, W1 plus W2 is a linear combination of the vectors V1, V2 through Vn. But the span of these vectors is the set of all possible linear combinations of the vectors V1 through Vn. Well, this is such a linear combination, therefore it must belong to W. And we're done. We took two vectors in our space, we've added them up and proved that the resulting element is also in our space. This proves that our space is closed under vector addition. Let's now prove that it is closed under scalar multiplication, and the proof is actually even easier. Well, what do we take? And again, the name gives it away. We look for closure under scalar multiplication, so we take a vector of our space and a scalar, an arbitrary real number. Call the vector CW. And the real number, you can call it anything you want. Lambda, K, A, B, doesn't matter. I'll call it K. So K is an arbitrary real number. And what do we want to show? We want to show that if we multiply the vector, W, by the real number K, the resulting element is still living inside of the space W. So if we do K times the vector W, so therefore perform a scalar multiplication, hopefully the space is closed, and so the resulting vector is still living inside of our space, so it can't escape W. Let's prove it, right? So K times W, well, by assumption, W is a vector in our space W, And our space is a set of all linear combinations of these n vectors. So let's assume that W is equal to, say, C1v1 plus C2v2 plus up to Cnvn for some choice of real numbers C1, C2 through Cn. Well, we can distribute by k, and we'll have kc1 times vector v1 plus kc2 times vector v2 up to kcn times vector vn. But if you look at this, we have expressed k times w as some multiple of v1 plus some multiple of v2 up to plus some multiple of vn. Therefore, kw is a linear combination of the vectors v1, v2 through vn. But the space W, once again, was the set of all possible linear combinations of these n vectors. And as kW is a linear combination of these n vectors, it is in W. Therefore, the space W, which is the span of n vectors from the vector space V, as it is closed under addition, closed under scalar multiplication, is, by the subspace theorem, a vector space in its own right. As we have just shown before, if you ever have a subset of a known vector space V, and this we knew was the case, because again the vectors v1 through vn were in V to begin with, and because V is closed under addition and scalar multiplication, any linear combination of these n vectors is a vector in V. So we had a subset of V. Therefore, by the subspace theorem, we only have to prove that W is closed under addition and closed under scalar multiplication. And we have just done so. Therefore, by the subspace theorem, this is our conclusion: W is a vector space. So W is a vector space in its own right. It is a smaller vector space living in the larger vector space that is V. So this is again our first example of the subspace theorem. And again, you can appreciate why it is so nice, because instead of proving that W is a vector space by verifying all 10 axioms, we only had to check the first two axioms, the closure under addition axiom and the closure under scalar multiplication. And keep this fact for now, since we've proved it in full generality. Keep this in mind for future references. If you ever are able to express a space of elements as the span of known elements from a larger vector space, automatically the span of these n vectors, for any n, is a vector space of the larger vector space V, therefore is a vector space in its own right. So if you can, or if you are ever asked whether or not something is a vector space, and you can show that it is the span of elements that you know are from a larger vector space V, you're done. The span of these vectors forms a vector space. In our next video, we will consider similar questions. The questions will be to decide whether or not W is a vector space, and we will use the subspace theorem. So we will observe that our set is a subset of a known larger vector spaces, and we have 5 of those. And then we'll simply have to check the two axioms, closure under addition and scalar multiplication. If the two axioms are satisfied, we do have a vector space. If one fails, we do not have a vector space.